Creating novel views from a single image can be done by unprojecting depth information from an old image into world space and back to a new image with a different camera matrix. This technique, also known as warping, has a lot of use cases, such as temporal upsampling, subsequently added 3D vision, or latency reduction within a client-server setup used for remote rendering. However, reprojecting RGB depth images causes artifacts within the specular parts of the image. As you will notice, reflections appear as painted on the reflecting surface. Here, an extrapolation from a single frame. This leads to unintentional effects within several applications, like hopping and temporal upsampling, wobbling in latency reduction, or missing depth in 3D vision. We propose a technique to synthesize novel views from layered RGB depth images that also support specular effects. Let me display our concept assuming a powerful render server, which is capable of computing a large number of ray intersections in real time, and a thin client where the user interaction takes place. The render result is split into one RGB depth layer for the diffuse and one for each specular component. In the case of reflective and refractive layers, the depth encodes the ray length between two light bounces. The layers are transmitted to the client and give us the input for our algorithm. At first, we unproject the diffuse information into world space. As shown previously, this is sufficient for us to compute the image flow. We then reconstruct the screen space normals by differentiating the diffuse depth component, which is needed to unproject the reflective and refractive layer. We now have all the information we need to compute the reflective and refractive image flow. This step is our main contribution and will be shown later in detail. The RGB components are then warped individually for each layer. By using a push-pull method on the texture's bitmap levels, undefined regions are filled with surrounding color information. Finally, the layers are composited to the output result. Determining the specular flow is equivalent to finding the vector from a source pixel in the old image to its target in the new image. In the specular case, this position cannot be calculated analytically, since there is no functional description of the surface geometry. Hence, we have a different way to get this information. From the specular unprojection, we know the world position from the deflected ray for many surrounding pixels in the old image. We now want to find the source pixel that stores the color information we would see in the specular share of the target pixel. For this, we calculate a reference vector by the specular function and the reprojected position and normal as its parameters. The angular distance between the target reference vector and the vector to that source world position gives us the quality function we need to optimize. We investigate the smallest angular distance using the gradient descent method, starting with a good initial guess that depends on two key positions. First, the diffuse flow origin, which is also the solution for infinitesimal short deflected rays. And second, the solution for assuming a planar surface. The key positions are blended with their quality function. On our test system with a mobile GPU, the procedure takes 18 milliseconds on the whole. Hence, it is suitable for real-time applications. Here are some of our results. Thank you for watching.